So let's take iris. Okay, and let us create a new variable called species versicolor, and this checks if species is versicolor, and if so, it gives it a 1, otherwise it's a 0. So if species is versicolor, this new variable, this new feature is 1, otherwise it's 0. And then we can do this also for species virginica. So if species is virginica, then give it a 1, otherwise give it a 0. Now we do not need to do it once more for the third species, because if these are both 0, that means that the species is actually setosa. So these two variables are actually enough to encode all three species, right? If this is 1, then it's versicolor. If this is 0 and this is 1, then the species is virginica. If they're both 0, that means that the species is setosa, because it's not versicolor, it's not virginica, and there's only one other species. I hope you understand what I'm trying to say here. That's pretty cool. If you're to run this, there we go. And we can now actually remove the species variable. And there we go. We replaced that one variable species with 2. So species versicolor and species virginica. And see, in this case, since the species here in these rows is setosa, that's why they're both 0. So there are 3 representations actually: 0, 0, 1, 0, or 0, 1. Now that we, worked on an example using the iris data set, let's go back to our data, train, and then imputed, right? So we feature engineered a new column, and then we've imputed the mass and the height, or we removed rows for height and gender, and we've imputed mass and BMI, and now we have this data set. This is a categorical variable, so we want to encode it. We can see from schemr, that gender contains 2 unique values, 2 unique options or possibilities. So if we want to use one-hot encoding, remember how we had 3 possibilities for species and iris, and so we only needed 2 columns. So in this case, we have only 2 possibilities, so we only need 1 column. So we would mutate, and let's call gender masculine would check if gender is equal to masculine, and if so, it would be 1, and if it's not masculine, it would mean it's feminine. In that case, it would be 0, and there we go. And then we can actually, again, remove gender, and there we go. We have, so this is feminine, this is masculine, 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 so on and so forth. So we replaced that categorical variable with a numeric one, and we can save this as data training imputed encoded. Okay, there we go. Data training imputed encoded, and there we go. Okay, I hope you're realizing that none of this is random, right? We're step by step organizing and arranging our data set, right? Initially we didn't have this column, we created it, and then we had a bunch of missing values, we dealt with those, and then we had categorical variables, we dealt with those. Now we have a completely numeric data set, but you can see that the numbers are all over the place, right? These are all below 0.00 or 0.01. They're very small numbers, whereas height are very big numbers, and mass are like in the middle, and then we have just 0 and 1. So we want to standardize or scale all of these to be on a very similar scale. So now let's talk about feature scaling. and we can go ahead and collapse this. So we've done feature engineering, missing values, dealt with missing values. We've encoded categorical data. Now it's time for feature scaling. So for that, let's create a function called normalize. And this takes in a feature, and essentially it takes the feature, subtracts from it the mean of the feature, and divides it by the standard deviation of the feature. So this is just a formula. You can just memorize it. This is how you would normalize a set of numeric numbers. You take the mean of those numbers and you subtract the mean from every one of those numbers, and you take the standard deviation of those numbers and you divide what you just did, subtracting the mean from each of them. You divide it by the standard deviation, and that gives you a normalized set of numbers. And remember, normalization is where the mean is 0 and the standard deviation is 1. So if we do this to every one of these features or these columns, we're essentially going to normalize them all to all have the same mean and the same standard deviation. So let's run this so that we get the function saved into our environment, and then we can take our data training, imputed, encoded, and let's mutate all. And we can do this safely because of our previous step where we encoded or vectorized the categorical variable. We can now just apply the normalization to all of them because they're all numeric, right? We don't need to worry about it. Mutate all, normalize. And normalize here refers to our function here that we just defined. And if we run that, there we go. Now they all have the same mean and the same standard deviation. They're all within the same range, which is very cool. This is very clean data, and it's very ready for machine learning algorithms, for mathematical algorithms, for computers basically to process. Let's save this under data training, imputed, encoded, and normalized. Okay. There we go. Okay. So now that we've completed all these steps, let's create a complete pipeline. Complete pre-processing pipeline. Now you see how we've been saving them all with each step, right? The first step was imputed and then encoded and then normalized. We don't need to do that. I'm just doing that just to show you each step clearly. But what we can do is we can actually do it all in one single pipe, in one single step. So to do that, let's start with what we initially started with. So the first step we done was feature engineering, right? So we started with, and actually let me just, I don't know why that's stuck here. Anyway, so the first step we had here was this step. So let's take this and let's collapse this. So we start with this step. So this step creates a new feature. And then the next step after that was dealing with missing values. So what we did was we dropped the missing gender and height, and then we also imputed missing values for mass and BMI using the mean. So let's take that. We pipe the result of this into that. So here you see we have a missing value. We run this, and now we don't have a missing value. And then the next step after that was encoding categorical data. And we encoded the gender variable. So let's go ahead and add that. There we go. This is encoded. Okay. And finally, we normalized or scaled the features. And that was done using this step. So we can just add that here. There we go. If we run this, you see all the steps are here. It's a single pipeline. So we're creating BMI, we're dealing with missing values here and here, and then we're encoding categorical variables, or vectorizing them, and then we're normalizing them. And so we start with this training data here, that's like this, and we end up with this, which is a very nicely pre-processed and ready for machine learning version of the initial data. That's the complete pipeline, which is pretty cool in my opinion, right? There we go, right? We can save this data train pipeline, and to check to make sure that this data train pipeline is the same as what we have here, which is data tr imputed, encoded, normalized, we can use a package called Waldo. So let's go ahead and install Waldo, and here we can compare them. So library, we don't even need to load it, we can just use Waldo. Remember, the double colon allows you to use the namespace of the Waldo package, so without having to load it. Compare, and we want to compare data train pipeline and data train imputed, encoded, normalized, and we run this, and there we go, there are no differences. So these two are exactly the same. This one just involves a bunch of steps saved as different variables, and this one does it all in one step, in one pipe. Now, before I end this video, I want to very quickly show you how you can do all of this in a much more concise and cleaner way using a package called recipes. So install packages recipes. Do you want to just no, let that install. So recipes actually provides you with functions for doing each of these steps without you having to deal with using deployr to like mutate or to drop or to select and that kind of stuff. So okay, that's loaded. So recipes, we load recipes. So because recipes is somewhat of a new package, you might encounter issues, which don't get worried, they're easily fixable. You see, I tried to load recipes and it said that a package called generics is at version 0.0.2. That's what we have, but we need 0.1.0 to use recipes. So what I did was I just reinstalled generics, which updated it to version 0.1.0, and then I reinstalled recipes, and then now we're working. It's working. I was able to load recipes. So don't worry, everything is fixable. Let me just go ahead and close all of these up here. Okay, so we have recipes loaded. If you go into here, recipes, step, okay, there we go. So these are the steps, the different pre-processing steps you can do with recipes. Some of them might look familiar. Median impute, right? Mean impute, imputing with the mean. Okay, and then impute, we covered that in the slides. And different ways of pre-processing the data, downsampling, creating dummy variables, that this is the encoding function, etc. So let's go ahead and use these to replace everything we did here with recipes. So we start with the data train, and the first thing we have to do is we have to create a recipe. To do that, we use the recipe function. Okay, so this is the first thing you have to do. You create a recipe, and then the first step we did was we created a BMI variable, right? We did some feature engineering. So we can use step mutate. So step mutate is from the recipes package. BMI equals mass divided by height times height. The next step is to remove rows that contain missing values for the height and the gender variables. So step omit, we would call, or NA omit. NA omit for which variables? Height and gender. And then we want to impute using the mean any missing values within the mass and the BMI variables. So step mean impute we would use, and you can use median impute as well, but we're using mean impute. And we do that for the mass and the BMI variables. And then we want to encode the categorical variable as dummy variables. So we want to do one-hot encoding. That's done using dummy. And we want to do that for the gender feature, gender variable. And finally, we want to normalize everything. And then we want to prepare this recipe. So for every recipe, you need to start it with recipe and end it with prep. And these are all the different steps. And you can add as many steps as you want. And each step, you specify which column it should apply to. Now, if we were to run this, we get a recipe and it gives us a description of it. Inputs, there are 4 variables, and the training data contains 66 data points and 22 incomplete rows. And the operations that we follow are variable mutation for BMI, removing rows with NA values in height and gender, mean imputation for mass and BMI, dummy variables for gender, centering and scaling for height, mass, BMI, and gender masculine. So it gives us a very nice description, a recipe basically, of all our preprocessing steps, which is very cool. Now, we can save this as a recipe. Let's save this as data recipe. And we can juice this recipe. So juice the recipe, and that gives us the actual processed data. So just the data recipe on its own is the recipe. It's a description of the steps, of all the preprocessing steps. And then when we juice it, we get the actual processed data, the data that went through all the steps. And to compare to make sure that this is the same as data train pipeline, or even data train imputed, encoded, normalized, we can use Waldo again. Compare. Let's save this as data preprocessed. Data preprocessed. And data, what was this called up here? Train pipeline. No differences. And we can even compare it with this. Again, no differences. So this actually essentially, allowed us to do in a much easier, much more concise way everything we did up here. So that's recipes for you. I will see you in the next videos.